This is the third part of the video on the chapter on related rates, and we're going to look at example 279, parts A and B. And here the situation is we're given the height of a person is 6 feet, the lamp post is 18, we're given the rate of change that the person's walking away from the lamp post, and we're being asked for the rate of change of the length of his shadow. So, again, draw a picture, label the parts of the picture that you're either being given information about or asked information about. Do not put constants in for things that are changing. The height of the lamp pole is not changing, it's a constant 18 feet. The height of the man is not changing, it's a constant 6 feet. We're given the rate of change that he's walking away from the lamp post, so this represents his position right here. And we're asked for the rate at which his shadow is increasing. So the light is coming through here, hits his head, casts a shadow. And so this is the length of the shadow on the sidewalk. And we want to find the rate of change of y with respect to time. So we're going to use similar triangles. So the large triangle and the small triangle are right triangles, and they share an angle. That means that this angle and this angle are congruent. Those two angles are congruent, and so we have similar triangles. That means that we have some proportions. We can take this side of this large triangle, which has length x plus y, and divide by the length of the corresponding side of the smaller triangle, which is y. So we have x plus y divided by y. That ratio is the same. And so we look at the corresponding sides here. The large triangle has side length 18, the small triangle has side length 6. So x plus y divided by y is equal to 18 divided by 6. We're using similar triangles. We'll use similar triangles for this. We're going to use similar triangles for part B, and for the example for video part 4 that I'm going to do next. So we have this equation. Multiply both sides by y. Now we have x is equal to 2y. So now we'll take the derivative with respect to time of both sides. So we have dx dt. The derivative with respect to time of 2y. So we have dx dt is 2 dy dt. We're given dx dt is 3. We're going to solve for dy dt. It's 3/2. So the length of his shadow is increasing at a rate of 3/2 feet per second. Now, for part B, we're being asked for the rate of at what rate the tip of his shadow is moving away from the light pole. So this part here, this x plus y, which I labeled as z, and I did that in the notes as well, we want the rate of change of z, because this is the distance as the tip of the shadow is from the light pole. So we want this rate of change. There are two ways to do this. I did this one way in the notes. I'll show you a second way to do this. So first we use similar triangles. So again, this z divided by y, the corresponding sides, is equal to 18 divided by 6, because we have similar triangles. That means that z is 3y, dz dt is 3 times dy dt. dy dt we calculated in part A. So this is 3/2 times 3. So we sort of have a related rate question inside of a related rate question. So we had to know dy dt in order to do this. So if we didn't have part A, we would have had to have found this rate of change first. And so now we just substitute our 3/2, and we have 9/2 feet per second. That is the rate of change of z. This is the way that the problem is solved in the notes. There's another way to do this though, and that is z is simply x plus y. So we write z as x plus y. Take the derivative with respect to time of both sides. dz dt is dx dt plus dy dt. These two we know. The dx dt we were given, the dy dt we found in part A. And so again, we just add 6 halves plus 3 halves is 9 halves. But again, the only way to do this was to solve for dy dt first. We did that because part A told us to. Sometimes we're simply asked for the dz dt without being told to find dy dt. So if that happens, then we have to find the dy dt first. And so again, sometimes you have a related rate question inside of a related rate question.